Problem number 15. Sine of y equals to cosine of x. Find the derivative at the point pi over 2 and pi. So we begin by taking the derivative of both sides independently. The derivative of sine of y is cosine of y times y prime. The derivative of cosine of x is negative sine of x. And now we solve for y prime. And we're going to go ahead and plug this in for x and that in for y. So y prime is negative sine of pi over 2 cosine of pi, and that equals to, in a unit circle, here is pi over 2. Sine at 90 degrees is 1. This is 180 degrees. Cosine at 180 degrees is negative 1. And we have an answer of 1, which is option C. Okay. Number 16. The function is x cubed minus x. We begin to identify its local extrema by first finding the first derivative, and we set the first derivative equals to 0 to find its critical points. Once we divided both sides by 3, we're going to get x squared equals to 1 over 3. And when we take the square root of both sides, we get plus or minus the square root of 1 over 3, like that, which we can then simplify to plus or minus radical 3 over 3. So we have two options, rad 3 over 3 and then negative rad 3 over 3. We then create a sign chart. So negative rad 3 over 3 is over here, and rad 3 over 3 is over here. These are the point where the derivative equals to 0. And we pick a test point. So if you pick a test point, if you did it correctly, this is a positive sign, these are negative derivative, and these are positive derivative. So which of the following option is true? We know that this point is a relative max. This is a relative max. This is a relative min, right? That's a relative min because it goes from negative to positive. So with all our answer options, we know that we just pointed that this is a relative min, so that's not true. This is a relative min, that's true. And then none of these 3 applies, and therefore our answer choice is B. Okay. Number 17. The function f of x equals to x to the n. And so to identify inflection, we need to find the second derivative of the original function. So we begin by taking the first derivative, and then we will be taking a second derivative right here. So we bring the power down and we subtract that by one more unit, and that's the second derivative. And so it says the graph of the function will have inflection point when n is either is it even or odd for all values, for no values, divisible by 3. So to investigate, we make up a couple of n values. So let n equals to 4. That's an even number, right? That's an even number. Inflection is the second derivative. And if n equals to 4, then you're going to have the second derivative is 12 times x squared. And to find inflection, you have to set it equal to 0. And then you solve for x, and x equals to 0. So a possible inflection point is when x equals to 0. Now, you also have to investigate and see if there's a sign change. So you will pick a test point to the left of 0 and a test point to the right of 0. And if you do, you will notice that there isn't any sign change. So when n is an even number, there is no inflection because the sign never changed. And if you let n equals to like an odd number, you're going to see that the second derivative is 5 times 4, so that's 20. And then 5 take away 2, that's 3. Okay. And if you proceed to find the possible inflection point, you also see that x equals to 0. We then create a sign chart, and we pick test point to the left and to the right. And if you do pick test point to the left and to the right, you will notice that there is a sign change between at 0. So there is inflection when n is odd. Okay, so you go back and you pick the fact that there's inflection when n is odd, which means that your option is B. Number 18. Number 18 says that a particle is subjected to gravity according to the following graph of the particle's velocity. So this is the graph of the velocity, guys, which is the graph of the first derivative. And at what time is the particle at its highest point? So in other words, the particle is moving up and down. It began in the middle and is going to move up and down. Okay. Or let's say that the particle began at the very bottom and is going to move up and is going to move back down. Okay. So in the first 3 seconds, the particle move up. So the particle move up in the first 3 seconds, and then it comes to a stop. It comes to a stop when time equals to 3. Okay. And then it began moving back down. And it came back down to the original, to the starting position at time equals to 6. So the question is, at what time is the particle at its highest point? Well, the particle is at its highest point at time equals to 3, because afterward it went back down. So we say 3. Okay. Number 19. The particle is moving to the right when, so we have this position function. And to analyze its movement, we need to look at its velocity, which is the first derivative. So we take the first derivative and we get 8t to the third minus, this is 12t squared plus 4t. We then set it equal to 0 because we want to know when it comes to a stop first. So we take the first derivative, we set it equal to 0, and then we try to simplify as much as we can. Notice that it is all divisible by 4, so we're going to divide those by 4. And also notice that I can factor out a t, and this is what I'm left with, okay? And now I'm going to continue to factor the inside, all right? And if you did it correctly, you should get 2t minus 1, t minus 1. And that means that your first critical point is when t equals to 0, your second critical point is when t equals to 1/2, and your third critical point is when t equals to 1. So then you draw yourself a number line. We call this the number line for the velocity or the first derivative. And go ahead and plot where the first derivative equals to 0, like that. And then you're going to go ahead and make the sign chart. Now, when you do make the sign chart, you're going to realize that that's negative, that's positive, and that's negative, and that's positive. Okay. So now we can answer the question, when is the particle moving to the right? The particle is moving to the right when the velocity is positive, and that would be from 0 to 1/2 and 1 to infinity, and that would be option D. Okay. All right. For number 20, it is a calculator problem. The acceleration is increasing when, so this actually requires that we take a look at the second derivative function, and once we know the first derivative, then go ahead and take the second derivative, and that gives you the acceleration function. Okay, and we're gonna go ahead and this is the acceleration function. To know when the acceleration function is increasing, we are going to graph. We're going to go ahead and graph the acceleration function. 24x squared minus 24x plus 4. Graph that. Zoom 6 for now. And we'll wait. All right. And we want to know when it's increasing. So if you look carefully, it's increasing from there all the way to there. That's when the acceleration function is increasing. So we're going to go ahead and calculate the minimum value. Second, calculate the minimum value. Pick a left bound, pick a right bound, take a guess, and we're going to see that it's at 0.5. So from 0.5 to infinity, that's when the function is increasing, and that would be option B. Okay, option B. Number 21. All right, number 21 says the circumference of a circle. So what we know here is that we know that the circumference of a circle is increasing at a rate. So the change in circumference over the change in time is 2 pi over 5. What we want here is we want how fast the area is changing when the radius equals to 5. Okay. So that's the information that we have. So notice that the circumference is increasing. Okay. How fast is the area changing? The area of a circle, how fast is it changing? So we have to find a relationship between area and circumference. We know that area is pi r squared, but that's so far a relationship between area and the radius. But we need to know relationship between the area and circumference. We also know that circumference is 2 pi r, so we can actually solve for r and then plug it in here. Once we do that, then we have established a relationship between area and circumference. So area is equal to 1 over 4 pi times c squared. Make sure you do that right, because I did it in my head. I square this and I square that, and I cancel out with one of the pi's. Okay. Now we differentiate. Remember that area increases, and so will circumference, and therefore they are both functions of time. So the derivative of the left side, we call it a prime. The derivative of the right side, we bring this down first, and that gives us 2 over 4 pi times c prime. And now we plug things that we know in. So we want to find the derivative of the area, the change in the area. We know that c is the circumference. C is the circumference. So if you know the radius, then you can find the circumference. Since the radius is 5, circumference is 10 pi. And this is the information that's given to us, which is 2 pi over 5. And now we're gonna go see what we get. So we get this is gonna be, you have 10 pi times 2 pi, that's 20 pi squared, and then you have 10 pi, so then you have 2 pi remaining. So the change in the area with respect to the change in time is 2 pi, and that is option D. Number 22. Okay. A conical tank has a height that's 3 times its radius. So before I write down what I know and want, I can quickly sketch the graph that it's the tank, the dimension of the tank that they describe. So they did say that the tank, the height is 3 times the radius. So if that's the radius, then that's 3 times radius. And also notice that the water is leaving the tank, right? So this model represents the water that's left in the tank after so much has left. We call this the height, and we also call this our radius. But I don't want you to confuse this radius with that radius, so why don't we call this x, and then we'll keep this a radius, okay? Now, we can begin by establishing a similar triangle relationship between these two triangles. So we set x over r, 3x over h. We cross multiply, we establish this relationship, okay? Notice that we can divide both sides by x, and the x would disappear. So this is our relationship between H and R. Leave that to the side for now. And let's go ahead and write down what we know and what we want. So what we know is that water is leaving the tank at a rate of 50 cubic feet per minute. So water is volume, so we know that the change in volume is 50 cubic feet per minute. Okay, what do we want? Well, we want to know how fast the water level is falling when the water is 3 feet high. So we want to know the change in the height when the height is 3 feet. Okay, so we write down how they're related, how volume and height are related. We know that volume is 1/3 pi r squared times the height. All right. So we're gonna express everything in terms of height. That means that we're gonna substitute in for the r. From this relationship, we know that r is h over 3. That's what r is. So we're gonna go ahead and replace r with h over 3. Square that, and then there's an h out here. Now, there's an h squared here, and there's a 9 at the bottom. 9 times 3, that is gonna be 27 times h to the third, because there's 3 h's there. So that's our volume function, and now we're gonna go ahead and differentiate, which I'll do it over here. So volume is a function of time, so is h. So the derivative of volume, we call that v prime. The derivative of this guy over here, you bring down the 3, so you can have, if you bring down the 3, it will cancel out with the 27. So what you have left is pi over 9 times h squared, because you take 1 away, you multiply that by h prime. Okay, so we're ready to plug in our information here. We know that the change in volume is 50. We know that h is 3. And then we're looking for h prime, because that's what we want. So we're looking for h prime. Okay. Now this is 9 over 9, so that will go away. As you can see, the change in the height is going to be 50 over pi. That's left over. And 50 over pi is about 15.915. That's 15 over pi. Okay? So your answer choice is C. Number 23. A function is continuous for all x and has a local minimum, so f is continuous and has a local max, local min at 1,8. We can maybe sketch a function that this is a local min, okay, which must be true. Which must be true, right? If you look at our graph, this is just a sketch. We know that this doesn't have to be true. We know that the derivative at 2 doesn't have to be 0. We do know that the derivative has to exist at 2 though, because it's continuous. So derivative exists everywhere. The graph is concaving down at x equals to 1. That is not true, because if it's a local min, it has to be concaving up, as you can see. And if it's local min, it says that the derivative is negative if x is less than 1, and the derivative is positive if x is greater than 1. That's actually true because if you look carefully at the graph here, you can tell that it's negative, it's positive. All right, that's another way to verify local min. And this says otherwise, so that's not true. So which must be true? It would be B and D. B and D must be true. I take that back, guys. The only one that's not true between B and D, because there can only be one answer. So the only one that's not true is actually B. B is not true. And here's the reason why. Just because it's continuous doesn't mean that the derivative have to exist. Consider the function. Say if I drew this function and it continued to go like this, and it has a vertical line here, and it turns here. When you take the derivative at 2, you're going to get a vertical line, and the vertical line is undefined. The vertical line has no slope, and therefore derivative does not have to exist at x equals to 2. So that's not true. So the only one that's true has to be D. Okay. Right. Number 24. At what point on the graph below are both the derivative and the second derivative less than 0? Okay. So this is the graph of the function. The derivative is negative when the graph is decreasing, and the second derivative is negative when the graph is concaving down. So if you look carefully at, say, point Q, that's when the first derivative equals to 0. So it didn't satisfy this condition. Point R, the first derivative is equal to 0, so it doesn't even satisfy this condition. Point S, the first derivative is positive, so it doesn't satisfy this condition. Point T, the first derivative is negative, and the second derivative is also negative because the graph is concaving down at point T. So our only answer that makes sense is answer E. Okay. So number 24, the answer is E. Right. Number 25. The limit as x approaches infinity of 6x squared over 200 minus 4x minus kx squared. And if it were to equal to 1/2, what should k equal to? What we have to do first is we worry about the left side while keeping the right side the same for now. That, okay? So if you take the limit as x approaches infinity on the left side, then one thing you can do is you can use the end behavior. When x approaches infinity, the only thing that matters is the term with the leading degree. So the only thing that matters is the 6x squared and the minus kx squared. That's because those are the term with the leading degree. All right? And the limit as x approaches infinity, we can continue to cancel out the x squared, and that leaves us with negative 6 over k, or 6 over negative k, it doesn't matter. And we want these two to equal to each other, and these two will equal to each other when k equals to negative 12. Think about it. Negative 6 over negative 12, isn't that 1/2? So you're done. So k has to be negative 12.